Oh, going to ask that only. So you can take permission from Dr. Harsh. Then
Good evening, sir. I'm ready and we can start whenever we are ready.
yes, please go ahead. Please go ahead now.
Okay,
Recording is
sure.
on. Okay, please.
Sure. Thank you. Good evening, everyone. It is my great pleasure to welcome all of you to the seventh day of 8 days long online international workshop on empirical methods in social sciences. I hope you all are excited for what promises to be an intellectually stimulating and enriching experience. I'm Dr. Neha Pandya, Assistant Professor from the Department of Banking and Insurance, Faculty of Commerce in Maharaja Sayajirao University of Baroda, your moderator for today's session. My goal is to ensure that each one of you have a platform to engage fully. Please do not hesitate to contribute. This workshop is designed in such a way where we all can learn from one another. Our esteemed speaker of today's session, Dr. Hersch Sahay, is currently working as an assistant professor in the Department of Economics, Pondicherry University. Before joining Pondicherry University, he worked at Narsi Monji Institute of Management Studies, Mumbai. Dr. Sahay is well versed with time series and panel data modeling using econometric packages like R, eViews, and others. He has been a resource person for numerous workshops on this topic. Apart from teaching, he is also involved in research in international finance, public finance, inflation dynamics, monetary policies, and more. His research work have been published in numerous reputed journals across the globe. There are two sessions today on an introduction of statistics, econometrics, and big data using time series econometrics with R and big data analytics with Tableau. Not delaying much, I now hand over the session to Dr. Harsai. Sir, please, you may take over.
Thank you, Dr. Neha, for that introduction. And I welcome all the participants once again to this session. And yesterday we were discussing about R. And given that we have only 1 hour of time allotted for the introduction to time series, what I will do is that I will very quickly give you a brief introduction of what is time series data and how is it different from cross-sectional data and panel data, and therefore why do we need specialized techniques to deal with time series data as compared to what we have for other types of data sets. And then I will work in R as I had promised you yesterday primarily, and we'll see the different techniques that we can use. So it's just an overview of sorts that I'm going to give. Now, when we are generally faced with when you are dealing with basic econometrics, what the type of data that you generally use is what we call as cross-sectional data, wherein the data is collected from various cross-sectional units, for example, from households, from various individual respondents, or from various, say, shopkeepers in a particular area. Now, all these type of data that we get are collected at a given point of time, and the various units from which the data has been extracted or collected are spread across geography or in space is the spread. And therefore, we generally call such data as spatial data or cross-sectional data. However, in time series, what happens is, as the name suggests and which you are very well aware, is that we collect data over a period of time on a particular variable. For example, if we are working with GDP, right? So if, yeah. So let me just share my screen. I don't know if I have got sharing permissions, right? Let me just share my screen. Is it visible to all of you? Can you please confirm?
Yeah, it is visible.
Thank you so much, sir. Now, let me open just one of the data sets. So I'm opening a GDP data set. It's now what happens is that when you observe the various observation on any particular variable, and we say that if it's a time series data, what happens is that we are observing the various observations or whatever is the value that particular variable can take at any given point of time, and the entire time is arranged in a chronological order. Either it can start from the most recent period to the period which is way back in time, or we can start from a time which is long back in history and to the most current period. Now, when we go to most of the databases, I don't know why is it not working. I think there is no problem with my number. 1 second. Let me close other. Yeah, so when we open various types of databases or whenever you come across time series data, generally you will see that the arrangement of data, you will find that it will be in the order where you will have the most recent data on the top. Say suppose data for 2023 followed by 2022, whatever is the value of GDP in 2021 and so on and so forth till 1950. Let's take that thing. But when we are actually doing our analysis, what we generally do is that we have to arrange the data, whatever, as many variables that we have. Say, suppose if we are working with 10 variables, all the variables, first of all, should be noted, is that in its basic form, all the variables should be of a particular frequency. Now, what is frequency? The number of times we get an observation in a given time period. For example, if it is annual data, we will get one observation every year. If it is monthly data, we'll get one observation on that variable for every month. If it is quarterly data, we'll get one observation of that particular variable. Let's take GDP for every quarter. And so on and so forth. We can have quarterly, monthly, weekly, daily, and then even per second data, like we have the data on seismic scales like earthquakes. Now, again, there is also a case that time can be either continuous scale or it can be discrete scale. So when we take a plot of ECG, many of us would have seen an ECG plot, what is it? It's basically a time series data plot itself. It's a time series of the magnetic impulses which are coming, electric impulses which are coming from the various nodes which are connected on our chest and body. So whatever heart gives us very minimal impulses. So a plot of that over a graph paper is what is ECG, right? So that is a continuous time series data. Nonetheless, in economics and finance, what we generally work with is what we have as a discrete time series data, where the data is distributed not on a continuous scale, but it is defined for every time period, the time period being either daily, weekly, or every 5 seconds, or every hour, or whatever be the frequency that we define. So a key property of any time series data, unlike cross-sectional data, is that it has a given frequency. Point number one. Okay. So whenever we are working with time series data, the various variables that go in a time series analysis should be of a particular frequency. If we are working with GDP, and if it is annual, I'm trying to build a model where GDP is a function of, say, prices, it's a function of exports, it's a function of, say, interest rates. All the other variables should be annual. Nonetheless, just to give you an idea, that nowadays, like in the past, I would say past decade or so, we have also started working with mixed frequency data, like what we call as a Midas analysis. Okay. So now we do have techniques available in time series econometrics, wherein we can use a particular data, which is one variable is annual, the other variable can be daily, the other third variable can be weekly, another variable can be even to the extent of even say hourly type of data. So that sort of analysis is also possible, and that is what we have right now on the frontiers of time series analysis. Okay. So that is point number one that has to be noted, that when you start your analysis, all the variables should be defined at a given frequency. Now, second point, and which is very, very important, is that when we look at time series, we can can you see my screen?
Yes, sir. PPT is on.
Yeah. So whenever we look at a time series, we generally talk about decomposing a time series in its components. And this is very different from what we have in the case of cross-sectional data, where we don't think of any sort of decomposition. In time series, we generally assume that any given time series can be decomposed into its components, into its four components. First is what we call as a trend component. So given any particular time series data, there is a general trend over which it might be changing. Now, I'm not saying that all time series data will have a trend, but it will have a long, like either it will be increasing over a period of time or it will be decreasing over a period of time. So there can be a positive trend or negative trend. So we can capture the trend separately. Then there is something called a cyclical component. So generally when you hear of business cycles, right? And what do we see? That crisis will occur over longer time horizon. So in 2008 we had a crisis. Then in 2012, 13 there was another some sort of a euro crisis. Then after that, around 2016, we felt some sort of a slowdown. And then eventually in 2020 onwards, there is a COVID crisis. So what happens? Generally, these type of business cycles wherein the economy will be going through a period of boom and then through a period of crisis or a trough are experienced over multiple years. And that is what we call as a cyclical component, which repeats itself over longer horizon time scales. Then we have a seasonal component. Now, seasonal component is also something which we can think of as a repetitive change. But the difference between cyclical and seasonal component is that, as we were saying, cyclical changes over longer time or longer number of years, but a seasonal pattern repeats every year. So every year, I don't know, let me just check if I have got the Excel file open. Yeah. I don't know why is it speed only. So as you can see here, I have quarterly data on GDP. And if I just take a plot of this GDP, okay, I'll take a very simple plot. And here, what do you observe? There is on the entire time series, you can see GDP is rising over a period of time, right? So that is a trend component. Now, within this, I'll go to decomposition in R just now. I'll show you. But there is some sort of changes that you can see which are repeating and that are very clear. So cyclical component is not very clear here, but what you can see is a repeating component. And as you can see, if I zoom in a bit more, what you would observe is that the patterns are getting matched. So the peaks are getting matched every time period. So if I point here, you can see it shows May 97. Okay, and these are quarter endings. So March, April, May. Sorry, April, May, June is the is the first quarter. Okay, so this is December, which shows December 96. Then this will be March 97. Here also, if I come here, so let me point out this peak. This peak will show as June 97. So that is quarter one, or I think this I will show you, the bottom part. Now, what do you see? This is September 97. So this is basically the second quarter of the year 96, 97, 98. I will bring my cursor here. Again, what do you see? September 98. So this is again the second quarter of 98, 99 financial year. Again, let me bring here. What do you see? September 99. So this is the second quarter again. September means second quarter ending. July, August, September of 99, 2000 years. So what do you observe? That every second quarter, every time the second quarter, the GDP is falling. And in the third quarter, it is rising. By fourth quarter, it is on the peak. And then again, it's somewhere in between the peak and the trough in the first quarter. Because we know that in businesses, generally what will happen is that by fourth quarter and all, whatever finances are left and consolidation has to happen, they will do, and the GDP will be on the high generally in the fourth quarter. So what I want to basically show you is that there is a pattern which gets repeated every year. And this is what we call as a seasonal component. And this is unlike the cyclical component, which gets repeated over longer time horizons. And then once all these components are split and removed, what we get is the irregular component, which is the most what do you say, volatile part, which is the most which is the part which we have to generally model. So in the entire time series analysis is largely focused towards modeling this irregular part. Okay. And finally, the last property which I want to tell you is that what happens, suppose for the year 2023-24, the value of GDP is observed to be 171.78 crores. Suppose. Now, this number could have been anything. It happens to be 171.78 lakh crores, but it could have been 170 lakh crores. It could have been 175 lakh crores. It could have been 180 lakh crores, right? So any value that you get of a particular variable at any point of time in the time series literature, what we call, is a random realization. In the sense, if I bring you here, now let me just hide this. Like 1 second. Now suppose if I have, let's take 1991, 1992, oh sorry, and I just have created some random years that I have written. Now the value of, let's take a variable x, and x, since it has been, the value of x will be arranged over a period of time, it will be called as a time series data, right? In its very basic sense. But the idea is the value which x takes in 1991, what value will it take? Do we have any confirmation on, or do we have any surety that the value of x, be it anything, let me make it more real. Let's take GDP itself. What example we were taking? The value of GDP in the year, if GDP is defined in lakh crore rupees, lakhs of crores rupees, will it be 2 lakh crore, 5 lakh crore? Is there any definiteness? Can anyone tell me? Can I say with a surety that in the year 1991, the value of GDP would have been 5 lakh crores? Is it sure? Are you sure about it? No, right? So it can be 5, or it can be 10, it can be anything. Now, since we are sitting in 2024, I can say with a surety whatever was the value of GDP in that year. But if I want to talk about what will be the GDP for 2024 in the year in which I am right now observing, can I say with a surety that it will be, let's take 180 lakh crores? No, I cannot say with a surety. Or if I want to talk about 2025 GDP, can I say with a surety that it will be 200 lakh crores? No, I cannot say that with a surety. Therefore, whatever observations of any time series data that we get at any point of time is a random realization. Okay. And if we assume that all the observations, let's assume that there is a machine. Okay, there is a machine, and that machine has one small display and a button. Every year, I'm playing a game, and therefore every year what I do, I go and press that button, and the moment I press the button, the display shows me a random number. We call it as a random number generator. And whatever number that appears on that display is I'm writing here. Okay, let me write some number. So every time that I am generating these values, these are random values which are getting generated. Now, please understand that the value 5 is coming from a random distribution. There may be, say, 1 lakh values, out of which one number is randomly chosen and kept for the year 2091 GDP value. Similarly, there will be another 1 lakh values, out of which one number was randomly selected and put here. Now, if the same exercise gets repeated for every year, in the entire time series that we have, what happens? If we are able to say two things. Point number one, that all the distributions which are giving rise to these random numbers are the same. Point number one. All the random distributions which are giving rise to these random numbers are same. And point number two, that we are able to identify the characteristics of that distribution. If it is a normal distribution with whatever is the mean and variance, or if it is a say a beta distribution with some shape parameter and position parameter. Now, if we are able to track or find a way to understand the behavior characteristics of that particular distribution, which is basically giving rise to these numbers over a period of time. And we have, let's take from 1951 up till 2023 GDP data I have. And if I am able to find a method to characterize the data distribution or the table through which these numbers are getting randomly generated, can't we make prediction about the future? The idea is that if I know that the way in which data has been randomly generated for 1951, how it has been generated for 52, 53, 54, 55, and so forth till 2023, if I'm able to predict the random number generator, that machine that I had, with some probability, I'm not saying with 100% probability, with some say 96% probability, I know that this is the way the machine works, which will give me numbers at every point of time. Can I not use my understanding of that machine to be able to tell what will be the GDP value for 2024? Or what will be the GDP value for 2025 and so forth? And this is what we call in econometrics, time series econometrics, as the data generating process. Okay, so data generating process is basically the as the name suggests, data generating process. So you can call that machine that I was talking to you about as the data generating process. And what does it do? It basically generates numbers. Akka, or 1 second, please. Akka, கொஞ்சம் தண்ணி கொடுங்கம்மா. ஒரு பாட்டில் கொடுத்துறீங்கண்ணா. So what happens is that at every point of time that we observe the values, if we are able to track the behavior of this time series, that will it be rising, will it be falling, what will it be behaving in a particular way, if we are able to track in a very definite way, we can make predictions, because most of the time series analysis that we do are centered around two things. Are centered around two things. Either they are around the way that you do in basic econometrics to try understanding causal relationship. So what is the impact of inflation on GDP? What is the impact of interest rates on inflation? What is the impact of rainfall on, say, crop harvest? All these things, that is objective number one. Objective number two is to be able to make prediction of the future values of any time series. Okay. So in order to achieve the second objective, which is making predictions of the future value, it is very necessary that we are able to understand the data generating process, or the process by which the variable has evolved over a period of time. And in order to understand how has the variable evolved over a period of time, there are certain methodologies or set templates that can be used. Okay. Now, this is almost the second last slide, maybe, which I will show you, and before we move ahead. Now, these are some of the basic templates that we have. Now, what you understand, what is a template? It's a stencil that if I know that I have a stencil, and if I observe any particular variable and it behaves like one of these templates, I am sure that GDP or say that particular variable will be of this type, and therefore I can characterize the behavior of that process in a particular way. Okay. Now, the one is white noise process, second is stationary stochastic process, and the third one is a random walk process or a non-stationary process. Okay. What I was talking to you about yesterday. So I will talk about that. And the next thing that we must also understand, I was talking to you about autocorrelation yesterday, right? And Durbin-Watson test is basically meant up to check first order autocorrelation. Don't get troubled by this equations. Don't get troubled. I'll make it very simple for you to understand. Now, Durbin-Watson test was only there to check if UT is related to its just immediate past. But in time series, you know that if there is a shock, let's take Reliance announces a bonus share yesterday or at 11 p.m., 11 a.m., sorry, 11 a.m., Mukesh Ambani has convened a AGM meeting, and they announced we are going for 1:1 bonus issue. What will happen? The impact of that one announcement on the share prices of Reliance will be lingering for periods together, as in for the next, say, 2 months, 2 days, there will be an impact, or even for a week or so, the Reliance shares will be picking up. Now, in that case, what happens? The impact of a shock which had happened long period back can be felt after, say, 5 periods, 10 periods, 20 periods even, right? So in order to check such long, like higher order autocorrelation, we rely on what we call as a Leung-Box Q test. Okay. Now, Leung-Box Q test not only checks for first order autocorrelation, but it also checks for higher order autocorrelation, which is of the order of K, where K can be any finite number, starting from 1, 2, 3, 4, 5, 6, whatever be the order of autocorrelation. So suppose if current shock has an impact after 5 periods, or after 20 periods, also the impact is felt. Okay. Let's take the announcement of Reliance bonus issue today has an impact even after 1 week. So what happens if I have daily data on Reliance Industries RIL equity prices, closing equity prices? There will be some level of autocorrelation observed over the 7 periods, because the shock of positive news had occurred today, but its impact is felt even after 7 days, right? So we rely on Leung-Box test, and Leung-Box test is also a very key way to characterize one of these phases. So white noise process, as the name suggests, is one where there is no autocorrelation. Okay. But in stationary stochastic process and non-stationary process, there is some level of autocorrelation that is observed, which can be seen through the Leung-Box test. Okay. I'll skip all these things and I'll open R now. And I'll show you how to work with load a time series data, do some decompositions, show some plots. Now, one thing is very important to understand is that whenever you are working with any time series data, the first point is always to understand the properties of that time series data before we use it for any analysis. And first property is always frequency. What is the frequency of the data? Is it daily, monthly, quarterly, annual, whatever it is? Second thing that we have to understand is by plotting it. So what I'm going to do is that I will import a time series data in R, prepare it as a time series data. I'll import a raw data, prepare it as a time series data. I'll show you some basic things that we can do. Okay. Now, since we had paucity of time today, what I'm going to do is that I'm not writing any codes. I have written codes with me, which I will execute. And I will give a copy of all these commands and codes I'll share with you so that you can play around these codes. These are all, since R is free and open source, my codes are also free and open source. If you wish, you can cite if you are using them for any workshop, or you are taking classes anywhere, or you are using for your analysis, you can just give a citation or acknowledgement. That should be sufficient. If you are not giving, I don't mind also. Then fine. So what I'm going to do is that in line number, I'm starting with line number 156, wherein I'm using a command to upload a particular or read a particular file. Okay. So whenever I'm reading a particular file, I had shown you one of the methods. So in R, one particular operation can be done in at least 3 to 4 ways. Even it may be 10 different ways that can be done. So don't think that one operation can be done in only one way, because I might create a function. You might also create a function for the same thing. Someone else might be creating a function for the same thing. So there are 10 different ways of doing the same thing, and everything is correct. There is nothing like one is wrong, one is correct. Okay. So one method was going to import data set and importing. Other method is using the function which is called read.table. Read.table is used to import text files. Whenever I'm storing data as a text file, For example, I have a data here. There is this, yeah. One second. Yeah. So I have a text file here. I'll use GDP QT. Do I have a text file? Yeah, QT. Yeah, this one I will use. Okay, I will now. I'll start from here. Line number 156. File.choose, what does it do? Is that it opens that browser for me to select the file. And comma T, when I'm writing, it basically tells that if I open this one, just to show you, the first row contains the labels which indicate what is what is there in row number 2 and onwards. So the first row, if it contains labels or the headers of the variables, then what I have to do is that I have to use this T, which basically stands for true, if headers are there or not. Suppose if the data is something like if this particular first line is not present and my data is only like this first line is absent. If this first line is absent, then header equals to true need not be given. But since it is there, I have to give. Getting back to R, I'll just call this command. Now, what happens when I have called this command? You can see this sort of window has opened. I'll browse to the place where I have kept the data set. JKEA. What is happening? GDP AN text. Now you can see the moment I have called it. Let me clear this. So there's a broomstick, Harry Potter's broomstick on the top. If you click on this in the environment, it just clears whatever was already present. So that is there is a task of this broomstick. Let me call it again. GDPAN. I'm selecting this file and I have got this data and it has been stored in an object called DA. Okay. Now the way that we have to use time series is we have to use a library. You remember I was using a library yesterday. So library T series. It's not coming. Do I have library T series already with me? Let me check in this list. If it is not already installed, it's there. Fine. So I think the R is malfunctioning right now. No problem. So I have loaded library time series, T series. T series is a package which is generally used for most of the operations that we do related to time series. Okay. So we have loaded time series and one function in this T series package is TS, and this TS function is mainly used for preparing a time series data or telling R that please recognize that this particular variable that I am telling you is a time series variable. Okay. Now, when I click on DA, you can see it appears $year and $. So dollar in R basically tells is a way of accessing something which is within a file. So within the DA file, that GDPAN, this file, what I'm doing, in R, I am loading the file and renaming it as DA. And in the DA file, I have two variables. One is year, the other one is R GDP MPA, which is real GDP at market prices annual. Okay, that is the variable. Now, what I'm calling is GDP A1 is defined as TS, the name of the variable which has to be converted as time series. So I'm calling DA, which is the name of the file in which the GDP data is stored. Dollar, put a dollar and this value. So what happens? If I just call DA, it does not know year has to be converted as time series or this variable has to be converted as time series. The moment I put dollar and call the name of the variable which has to be converted as time series, it will convert the GDP data as time series. And how is it converting? I told you there are one most important property of time series is it will have a time, starting time. So I'm telling what is the starting time, which is 1950. And I'm telling what is the frequency, which is 1 means being annual. So whenever I say frequency 1, which means it is annual. Now I have converted. And then what I can do, I can use the function which is plot.ts. Plot.ts, what does it do? It will plot a time series data for me. And when I call plot.ts, you can see on this window here, I have got a time series data for the GDP. And it has years on the time on the x-axis and GDP data on the y-axis. Okay, that is the GDP data. I will also show you a decomposition for the quarterly data. So let me load the quarterly data. So I have called GDP QT. I have here QT, yeah. Okay, the data is loaded GDP QT and it is stored in DQ. Okay, it contains, what does DQ contain? It contains quarter and it contains RGDP MPQ. Now, when I'm working with quarterly data, please understand what I have to specify. Start, but quarter will contain the not only the year, but also the quarter number. So whenever you have to combine two values in R, whenever we have to combine two things, two numbers, two characters, whenever they have to be combined, we use the C function, combine function. C stands for combine. So I am putting, unlike the previous case where start was 1950, which is the year value only, here I'm saying it starts from the first quarter of 1996 and the frequency is 4. That means quarterly. Every year you will have 4 data points, right? Quarterly means 4 data points in a year. So I will execute. Again, this is a TS function itself. And now you see, you get quarterly data, right? Now, we can also, I'll show you how to save. So suppose you have got this data and now you want to keep it in R. You want to save this for your, say, in a paper, you want to take this particular graph. What you can do is that, do you see this in the plots window? Plots is a window here. You have something called export. You click on export and there is an option of save as image. Now here you can save very high resolution images and you have option of either you want to save is at JPEG, PNG, various image formats are available that you can use. Let me save it as a JPEG. What is the name of the file? Let me say GDP QTR, quarterly GDP data. And I can keep the width and height. So if I want to increase the width to a very large value like a high HD image, I can also do that. So let's put it 1024. Automatically the height gets adjusted, or let me make it more high definition, 1920. Automatically, approximately, these are basically pixels that are shown, and I can always update preview and save. And what you can see, this graph has been saved wherever I have saved it. Okay, mostly I think it would have been saved on my desktop. I'm not sure if it came on desktop. I can open the file location, file in Explorer. So this has come here. Now you can see this is a JPEG file, and you can now take it and put it in your Word doc, or you can put it in any of your Excel, PPT, wherever you want. And this is, even if I'm zooming in, you can see it's not showing any pixelation, right? Much pixelation is not, because it's a very high definition image. So R allows you to generate these high definition images and also save them. Okay. Now I was talking to you about this decomposition. So I'm using this package which is called TTR. So there is a package called TTR which I have already installed. You can install it by going to package and installing it, the TTR package here. Okay, you can type in TTR and you can get it installed. Since I already have installed, I will directly use library TTR. And in the TTR package, once I have loaded TTR, there's a function called decompose. Now, what does the decompose function do? It decomposes the given variable into its components. And generally, what do we have? There can be two types of decomposition. One is an additive decomposition, which basically says that uh, a given value of time series data is defined as trend plus cyclical plus seasonal plus irregular equals to the actual value. Or it can be multiplicative decomposition, where I can say that the actual observed value of the time series data at any given point of time is equal to the trend component into the seasonal component multiplied by the cyclical component multiplied by the irregular component. Now, most of the times when you have most of the time series data that we generally observe in economics and finance are additive in nature, are generally additive in nature. So I'm going to decompose the quarterly GDP, which I have just now I had shown you, into its components by using the function which is called decompose. So I'm calling decompose function, and it will be decomposing GDP Q1. What is GDP Q1? You remember, GDP Q1 is a time series TS. It's a TS object, or it's a time series data, which is for quarterly GDP. And I have decomposed it. And then what I can do is that I can, so you can see it shows that it has been decomposed. So my prompt is available, and it has been stored in a particular variable called BC GDP MPQ, and then I will take a plot of this. Now, what do you see when I have taken a plot of it? I can zoom to show you in a bigger scale. Now, what do you observe? This is the observed data. This is the trend which is in the data. This is the seasonal component. And I told you that cyclical component requires a different treatment for generally we use some sort of a filter for filtering it out, like HP. There is a Hodrick Prescott, Baxter King filters, which are more sophisticated. But generally, what we can find is that this actual data has been split into its three components. The cyclical is still part of the trend, is what I can show you right now. A part of there in trend and a part of there is in the random component. And here we have decomposed it. So many a times what happens when you work with time series data, which are generally quarterly or monthly in nature, you have to first remove the seasonal component and then work with the data. And this sort of decomposition helps you. That was the first thing. Now, till the time we are working with annual data, monthly data, quarterly data, there is no problem, because the frequency is given and you will have data at every time period. So there will not be any gaps generally. But many a times what many of you will be are generally interested in high frequency data, which is like the Nifty data, equity data. Now, these data sets that we generally get are very high frequency, for example, daily data. But you know that when we are working with daily data, does stock market function on a daily basis? Format used at start function. Yeah, no, sir, it can. Okay, I had left certain things. Any realization of that? Okay. Financial year, again, it depends on you. I can call it financial year. Like, for example, if you have data for the given year itself, like you don't have financial year, you can. So it all depends on labeling. For example, I can use the financial year starting as the year or financial year ending as the label. So it depends on what label am I using. There is nothing like we just have to tell what is the starting and ending. There is nothing about whatever is it financial year starting or financial year ending. If it is, let's take not financial but calendar year, then it has to be the year itself. So it all depends on the researcher what they want to do. Any realization of a stochastic process is one point is time series, yes. So at any given point of time, given that you have various stochastic processes, its realization is what we call as a time series. How to quote financial year, sir? Quote as in right here on the bottom is what you mean to say? That can be okay in the start function. That we cannot that R will not recognize directly. So the T series package does not recognize. We do have newer packages like Quant Mode and FinTS. There is another package called FinTS and Quant Mode, which do recognize such sort of cases. But generally, it does not recognize the financial year like we have, which starts from a mid of an year, April to March. That type of it does not recognize. So either if it is say 2023-24, you can write 23, and you can also put the data for 2023-24 next to 2023, or you can put next to 24 for the financial year ending, and then use it as the label. Okay. Now moving ahead, generally what we observe is we work with is this financial time series data, which is not very regular because what happens, stock markets do not operate on a daily basis. So the data that you will generally see will be with some gaps. So let me just show you an example data. Gosh. I'm working, but 1 second, let me just bring the screen closer to me. Where did it go? I'm unable to see that. This one. Now, what do you see here? The data set that you observe here are the closing, open, close, high, low for NSE data, and it starts from 3rd March of 2003. So what do you see? 3rd March, 4th March, 5th March, 6th March, 7th March, then 8, 9, there were holiday, 10, 11, 12, 13, 14, 15, 16 was holiday, 17, again 18 was holiday, 19, 20, 21. So there is a time series data, but it comes with gaps. Now, when you have such a data, which is coming with gaps, we cannot use the regular type of functions in R. And for that, we have something called XTS, which has to be used. Okay. So what I will do is that I will show you how to load and work with such sort of a high frequency data in R. And then I will finish with some plots. And the last thing will be about stationarity and non-stationarity. So what I'm going to do is that I'm using this library or package called XTS, which is used for handling high frequency time series data. Now, once I have loaded XTS, the way that I open a particular data set in R, which is a high frequency data, is used by using the function read.csv.zoom. Now, read.csv is basically telling that the given data set is a CSV data file. So you can see here I have stored the NSE data as a CSV file. This is Microsoft Excel, separated value file. Generally, that is the most preferred way of loading. So many a times when you are downloading your data from the various NSE website or anywhere, you can download it as a CSV file, which makes life slightly easier to be loaded in R. Nonetheless, Excel is also permitted, and that we can also do it. There is no problem. Second thing is that, so if you remember, I told you file.choose basically opens that window for me to choose the file. Index.column tells me that the date indices are available in which column of the file. So you can see the date values are there, or the time series component is there in the first column. Second, we have to specify the format in which the date is stored. So I have written here, as you can see, it is date dash month dash year, right? And year is full year. It's not 03, it is 2003. And therefore, I have given the format as dollar, percent D, which stands for date, percent M, which starts for month, and but percent capital Y, which stands for, hello, am I audible? Can you please confirm if I'm audible?
Yes, sir, you are audible.
Okay, because my R screen has stuck. So I just needed to see that if my entire screen has frozen or just R has frozen. What is happening here? I'm really sorry. Let me just trying to get back. Yeah, can you see it now?
Yes, sir.
Yes.
Yeah, fine. So I'm specifying the format in which date is there. Okay. So once I load this file, I call this line number 191. The moment I call, it opens the data for me. I open it from this one, NSC 1 CSV. And then what I'm going to do is that once the data has been loaded, I can click on environment and it shows me that if the data is loaded or not. It has been stored in DZ. I can come down and see, yes, DZ has been brought in. So DZ is available. Now, once DZ is available, I am converting this DZ, which has been imported into what we call as a XTS or extended time series object. So whenever we use this function as.ts, it is converting. So I can convert any particular variable into a different type of a variable. So it slightly seems complicated, but if I would have gone very like step by step, you would have understood. So I'm converting the data that I have downloaded into a time series data now. It's basically like that. Now it has been converted. Now the moment I called plot DZ, what is plot DZ? It is that data which I had downloaded. What do you see? 1 second, I'll go to plots. All the 4 variables that were there, open, high, low, close, they have been plotted together. The other way of plotting is what we call as a multi-panel plot. So instead of them coming as a stack, what I can do, I can use this function called same function plot, but I will be plotting with a multi.panel is equals to true. Now what happens in this case? Let me zoom it. It's not coming. 1 second, let me call it again. Yeah. Now do you see? So when we are using this multi-panel plot, it not only gives me a more intuitive sort of a plot that you can see here. So XDZ. So the moment, see, earlier I was plotting for DZ, but right now I'm doing for XDZ. XDZ is an extended time series format data, which gives me much nicer plot in its way. If I want to plot just one of them, suppose I want to plot only the 4th variable, which is low. So I can just call it XDZ, 4. So you can see this is a nice time series plot, which is available here. Okay, so these are some so whenever you are using any time series analysis, first of all, what you have to do, see what is the frequency of data. Depending on if it is low frequency like annual, quarterly, monthly, you can import it in R using the TS function, TS, okay, TS that I was using here. You can see here TS. When it was annual, frequency was 1. When it is quarterly, frequency was 4. When it is monthly, frequency is 12. But when you have high frequency data, you have to import it as a XTS object. And once we have imported any data, what we have to do is that we have to take a plot in order to understand its properties. Okay. Now, what do you observe here? It is increasing over a period of time. Okay. Now, whenever you see such a data which is increasing over a period of time, generally this is what we call as a non-stationary data. Because what happens in such non-stationary data, what is our stationary and non-stationary data? Just to give you a quick idea, is that for any given time series data, if we observe, okay, 1 second. If you see any data set which is like this, do you understand this? If it is increasing, decreasing continuously, in this type of case, in this case, or this case, or this case, all these cases, there is a particular mean value around which the variable, actual variable, value of the variable is lying. So it is either when it is increasing, when the variable is increasing its value, it is coming back to the mean. When it is decreasing in value, it is coming back to the mean. So whenever you find such sort of a behavior, which we call as mean reversion. So whenever you find the data is showing mean reversion, it is stationary in nature. But whenever you see a data which is of this sort of a nature, like this, or what you are seeing here, this is what we call as a non-stationary data, because what do you observe? It is not showing mean reversion. If it has increased, if it has deviated away from its mean, it's not coming back to the mean. Okay, so whenever there is no mean reversion, we call it as a non-stationary data. There are some questions. Okay, there was, okay, it was observability. Now, in order to verify if a given data, one is graphical verification, if it is stationary or non-stationary. But one of the most important or method of verifying if a data is stationary or non-stationary is basically using what we call as a unit root test. Now, I'm not getting into the entire mechanics of a unit root test, but just to give you a quick idea of a unit root test, it basically tries to check if the given data is stationary or not. So whenever a given data is non-stationary, it is equivalent to saying that the data contains unit root. Okay. Whenever the data contains unit root, it will be non-stationary. So remember this, whenever the data contains unit root, the data is non-stationary. Okay. If the data does not contain unit root, it is stationary. So testing for the presence of unit root is testing if the data is non-stationary. Okay. Now, what I'm going to do is that I'll quickly convert. So you understand that I've told that this is a non-stationary data. So I'll just show you an example of how to do unit root test in R. Now, what I'm going to do is that I will capture the closing price. So you remember there are 4 variables here, open, high, low, close. So I'm capturing the closing price in line number 206. So XDZ is basically the variable in which the data is stored. Okay. Now in XDZ, one of the variable is named close. So I am calling the close variable and storing it in another variable called NSC. So you can see the plot of NSC. I'm calling plot. 1 minute. Mm. 1 second. Yeah. I'm taking the plot of NSE. So you see that this is the plot of closing prices. Now, what will I do is that I can create some sort of returns of this series. Returns is what is basically percentage change today's closing price minus yesterday's closing price divided by yesterday's closing price into 100. So this is what I'm doing here. Do you see this? So in time series analysis, when we want to take yesterday's, the last period, that is what we call as lag. So by using the lag function, I can capture yesterday's value of this NSE. So NSE is basically, it contains the closing prices. Closing prices means the Sensex, not Sensex, sorry, Nifty 50 closing prices of every day. And if I'm running line number 213, sorry, it is calculating the log of NSE value today divided by lag NSE means the yesterday's NSE price. If the default is 1, I can take 2 period lag, 3 period lag. Yesterday, you remember I had taken in Excel lag values. So the same way, lag function calculates the lag or the previous period's value into 100. Now, once I have calculated R, which is the lagged data, I can also show you, a plot of this here. Let me.
Sorry, sir, but
Hello? I
yes,
think.
sir. So, how much time will it take?
Hello, you're not audible, please.
Sir, am I audible?
Yes.
So, due to time constraint, how much time you will
Yeah, I'll
need?
just show you a plot of this and then I will get over
Sure,
here.
sure. Thanks.
Now, do you see this? This is the last thing, okay? So when I take the change in, so you understand what was NSE? You remember this particular plot? This was increasing over a period of time. I told you this is non-stationary because it is not coming back to the mean. But here when I take the same data and I take current value of NSE minus its previous value, what you see, what type of data we get? Now we are getting a data which is reverting to its mean. So now this becomes stationary, okay? So whenever you have a non-stationary data, by appropriately taking the difference of that data, like current value minus previous value, current value minus any period of previous value, you can convert a non-stationary data into a stationary data and use unit root tests for testing that. And in R, we have different functions. One is what we call as ur.df function. Then we have adf.test function. There are different functions for doing unit root tests, which we can cover maybe in further sessions where if we have on extended time series analysis. But to just give you an idea, time series, just to wrap up in a summary in quickly 30 seconds, time series data is different from cross-sectional data mainly because it is, first of all, arranged over a period of time, point number 1. Point number 2, it has to be understood that the frequency of data becomes very important to be understood and captured, even though we can work with mixed frequency data, but generally we have to take all the variables which are of one particular frequency. Third thing, you have to arrange the data in a particular order, as in starting from the most past to the most current in for all variables, or most current to the most past, whatever is the method you choose, it is permissible, no problem in that. Fourth thing that you must also understand is that before you start any analysis of time series, you must understand the data generating process of a given time series variable, which can be found by taking a plot of the time series data and then conducting certain basic tests like what we call as the unit root test in order to understand if it is stationary or non-stationary, because all the techniques that we have in time series analysis, first of all, depends on if it's a time series stationary data or if it's a non-stationary time series data. Because if you are using a particular technique, let's take a small, like any time series analysis tool is created in order to handle only a particular type of time series data, where it can be, say, let's take arch-arch models can be used, which are mainly used for working with such sort of high frequency data, can only be used with stationary time series data. But co-integration is another methodology which is meant only with working with non-stationary time series data. Okay, so we will get into those the world of tools related to time series analysis further. Thank you for patiently listening to my session today. And if you have any queries, I am typing in my mail ID in the chat box, and you can reach me for any queries that you have. And thank you for your patient listening. Thank you to all the organizers. Thank you.
Thank you so much, sir, for such an exciting section with hands-on on our studio. Now the forum is open for the discussion. Just know, due to shortage of time, we will only be addressing few questions. As sir have already told, if you have any other queries, you may write down to him.
Stationarity and normality are not the same, sir. There can be a particular variable which does not follow the normal distribution, but still it can be stationary.
Any more questions? We can take one or two more.
Meanwhile, I want to request all the participants, if they are in a position to open their camera. For this session, we want to take a group photo also. While people are having questions, they can ask it quickly.
Yeah, so if there are any further questions, you can drop me a mail and we can start with the next session. Thank you so much.
Hello, excuse me, sir. Hello.
Yes, ma'am.
Okay. Sir, my study is dependent on this tool only, stationarity test.
I'm unable to hear you clearly.
My study is dependent on stationarity test only. I used ADF test for performing stationarity test. My question is, after doing after performing the ADF test at first level, second level, the data changes. The variables that we have taken, original variables data, changes after performing the stationarity test. So after conducting stationarity test, I have used multiple regression analysis in my research. So the question is whether we have to use the changed data or the original one in regression analysis.
Okay, so please understand, if you are using a particular technique, let's take OLS for your analysis. OLS can only be used with stationary time series data. So if you have found that the given variable that you are using, for example, the NSE closing prices are non-stationary data, as I have shown you, it is increasing. But if you use OLS, let's take if you're using OLS, you cannot use the actual NSE closing prices, but what you will have to use is the transformed data, which is the returns of that, which is percentage change in the closing prices in your analysis. So depending on what analysis tool that you are using, you will have to use the data accordingly. Nonetheless, in the same line, if you are using, say, suppose co-integration method that you are using or ARDL that you are using, which supports non-stationary data, you can still use the actual data, which is non-stationary in nature.
So we can take one more last question.
Yes.
Thank you.
So I think there is no question.
Yeah.
Dr. Neha, you can proceed with the photo.
Thank you, sir. So moving towards the end of the first session, I would like to thank Dr. Firdaus Malik, convener of the workshop. My dear colleague, Dr. Bhagirat Baria, co-convener of the workshop, for giving me this opportunity to travel this enriching research journey as a moderator. I would also like to extend my gratitude to Team Jammu and Kashmir Economic Association and the Jindal Center for Global South. May I now request Dr. Firdaus Malik to share a few words with us. Sir, please.
So again, we are in between. So mostly I was giving the vote of thanks at the end. So let me take this opportunity to greet our esteemed resource person. Past 2 days with whom we are learning, or especially autocorrelation and multiple unity. Due to shortage of time, there are much more to learn. So I promise you all that we are going to have one fully workshop based on R from basics to applied, inshallah. So thank you very much, Dr. Hersch, for your valuable time and accepting our invitation at a very short time. And again, for our today's session moderator, Dr. Neha, for your time and availability and accepting. So
Thank you so much, sir. And thank you to all.
welcome.
Thank you.
So these are we are just learning. We are just trying to learn and master the econometrics and research. So we are looking forward for future opportunities to work with you all. Thank you very much.
Thank you. Thank you. Thank you so much. Thank you, Dr. Bhagirath, the co-convener, Dr. Virnos, the convener, Dr. Neha, the moderator of today's session. And I would like to thank all the participants. And I expect to see you all again in online or physical mode for many more future sessions. Thank you.
Thank you, sir.
Now we are going to join our second session on Jammu and Kashmir